we're going to look at a technique known as logarithmic differentiation here, which can be used when we have functions that consist of complicated products and or quotients that are raised to powers. Alright, so this technique is going to be called logarithmic differentiation, because what we're going to do is, our first step in this process is going to be to take the natural log of both sides of an equation. And once we do that, we can use our properties of logs to write the expression as a sum and or difference of logs, right? We just use our product, our quotient, and our power properties to do that. And then we'll just take the derivative with respect to x of each side of the equation. And that's going to involve using implicit differentiation, of course, because we're going to have to take the derivative of the natural log of y, right? But if you remember, the derivative with respect to x of the natural log of x, not equals. The derivative with respect to x of the natural log of x was just 1 over x. So when I take the derivative with respect to x of the natural log of y, I just have to use the chain rule. So I end up with 1 over y, but then I have to multiply that by dy dx, or y prime, which is going to be easier. And that second form that it's written in there, the y prime over y, that's going to be the easier form to write it in, because then what we're just going to do then is we're going to solve it for y prime, right? Because that's what we're trying to find. Y prime is dy dx, and that's what you're trying to find. All right. And then the nice thing about this is, how would we solve it? We would just multiply both sides by y, and since we originally had an expression for y, right, that was our original function, we can just replace y with that expression, and then we'll be finished. Okay. So here's a couple of problems for which you would want to use logarithmic differentiation. Okay. Now, again, is this the only way to do these, to take these derivatives? No, it's not the only way, but it's probably a much simpler way, rather than like in number 1 here, we could use the product rule. In number 2, we could use the quotient rule inside a chain rule, and so I mean, it's doable, but it's a little bit more complicated. So what we'll do is we'll just follow our process of logarithmic differentiation. So we would take the natural log of both sides here. So we'd have the natural log of y equals the natural log of this whole big expression. And now, since this is just the log of a product to powers, we can actually use our product and power rules of logs to rewrite this, right? Remember, the log of a product was really the sum of the logs. So this is really, and we can take the powers out front, right? So we can add these two logs and bring the powers to the front. So we would end up with 5 ln of 2x plus 1 plus 6 ln of x to the 4th minus 3. And this is still equal to the ln of y, right? I haven't done any derivatives yet. But now what I'm going to do is, now I'm going to take the derivative with respect to x of both sides of this. So when I take the derivative of the ln of y and the derivative of this whole mess, the left side, as I said in the directions up there, the derivative with respect to x of the ln of y, you can write in a simple form as just y prime over y, right? Because the general rule for the derivative of the natural log of u was u prime over u. But here, u is just y, so I end up with y prime over y, right? So on the right side, I use my derivative rule for the natural log. It's u prime over u. So the derivative, and again, the derivative of a sum is just the sum of the derivatives. So I would just take the derivative of the first expression and the derivative of the second expression. So in this case, I have a 5 out front in the first one, and then I would have u prime over u, which would be, the derivative of u here is 2 over 2x plus 1, which was u. And then for the second one, I have the 6 out front, and I would take the derivative of x to the 4th minus 3, which is going to be 4x cubed over u, which is going to be x to the fourth minus 3. And I'm almost done now, honestly, right? Because now I just would combine these into single fractions. So I'd have 10 over 2x plus 1 plus 24x to the third over x to the fourth minus 3. And that's now as simplified as it's going to get. And my last step, of course, is just to solve this for y prime. So how would I do that? I would just multiply by y on both sides. So I'm done, right? I've got y prime equals this big expression times y, and all I'd have to do, I just have to replace y with the initial expression for y, which is this. So yeah, this is going to be a complicated result, but it's perfectly fine. 10 over 2x plus 1 plus 24x cubed over x to the fourth minus 3. And I'm just going to multiply this by the original function. 2x plus 1 to the fifth times x to the fourth minus 3 to the sixth. And that would be my derivative. Okay. Now, is this the same exact expression I would get if I use the product rule? No, but it's equivalent, right? It would be equivalent. And I mean, I could use a bunch of algebra to get it into that equivalent form, but I'm not going to do that. Okay? I'm just going to leave it like this. And then the second one I would do in a similar manner. Okay? So the second one, I won't finish the whole thing with the second one, but what I'll do is at least start it out, right? This is the fourth root of x squared plus 1 over x squared minus 1. So it's really, if I initially take the natural log of both sides, I would have this. Again, all I'm writing is ln in front of it. I'm not really doing anything at this point. Just taking the natural log of both sides. But remember, the fourth root is really the 1/4 power. So the right side here can become 1/4 the ln of x squared plus 1 over x squared minus 1. And then this becomes 1/4. Now I would use my quotient rule, right? The log of a quotient is the difference of the logs. So it's 1/4 times the ln of x squared plus 1 minus the ln of x squared minus 1. And that's equal to the ln of y. And I could even go one step further here. I could even break up the ln of x squared minus 1 into the ln of x plus 1 plus the ln of x minus 1, because that's a difference of squares. But I don't even really have to do that here. I can just leave this in this form and now just take the derivative with respect to x of both sides. And then from there it would proceed in a similar manner as the other one. So I'll wait a few seconds and allow you to pause the video and try to work on this problem yourself. And the answer will appear shortly. And here's the result. You can see the steps that I took. I took the derivative with respect to x of both sides, and then I multiply both sides by y, and I end up with the highlighted yellow box. And of course what you would just do at the end then is, again, replace y with the original expression for y, which was the fourth root of x squared plus 1 over x squared minus 1. And this one I would definitely leave in that form. Because after I had finished the previous one, I realized, hey, you know, it's not really that much work to turn it into the same expression that you would have gotten if you had used the product rule, right? Because all that you have to see is this is just the sum times 2 additional factors. So I would just distribute those 2 additional factors, and what would happen if when I multiply the factors by the first term in parentheses here, the 2x plus 1 would cancel, and I'd end up with 10 times 2x plus 1 to the 4th times x to the 4th minus 3 to the 6th. And then when I distribute it, those 2 factors to the second term in parentheses there, the x to the 4th minus 3 would cancel, and I would end up with just 24x to the 3rd times 2x plus 1 to the 5th. And now x to the 4th minus 3 would also be to the 5th, right? Because that's one of those factors of x to the 4th minus 3 would cancel with that x to the 4th minus 3. So it's actually quite simple to see how the expression I originally ended up with is in fact equivalent to what you would have gotten by using the product rule.